Hello guys, welcome to my lesson on relative extrema and multivariable calculus. So we'll start off by the definition of relative extrema given by the textbook. So graphically speaking, once we find our critical points and we plug it into our function, we will be given a z value or a new height. And by the second partials test, we will determine whether this is a relative maximum or minimum or a saddle point. Now, how do we find these critical points? Well, just like in 2D, we can find these critical points by differentiating, except this time we partially differentiate the function in terms of x and y. To find these critical points, we must consider the definition given by the textbook. Now, using these critical points, we can tell whether these critical points are located in a relative maximum, minimum, inconclusive, or a saddle point. We do this by applying the second partial test. It goes like this, by this following equation right here. So once we plug in for this equation, we have four cases. We have first case where we find that we have a relative minimum. Number two, we find that we have relative maximum. Number three, we find that we have a saddle point. Or four, the test is inconclusive, meaning we have to come up with a different method to test for the relative extrema of the function. Now I want to talk about saddle point a little bit more, because saddle point is kind of interesting because it's neither a relative maximum or relative minimum. Because if you, let me just draw the 3D axes, right? The 3 dimensions. If we slice it in the x-axis, at this point we will kind of see that there will be a relative maximum. Similarly, we can also apply this with the y-axis, slicing the y-axis. And essentially, what happens here is that I kind of sliced it a little bit wrong, plus it's really horribly drawn, but essentially, we have a relative minimum. And so essentially the saddle point, it's literally just flat. It's like this, at that specific point. We can also see that we can apply it here as well. We can pretty much tell that there's a saddle point here, because we can, if we just like picture this as our critical point, we can, if we slice it, we can sort of see that this is already relative max, and then if we slice it from this angle, perhaps we see that this is a relative min. So yeah, based on this, based on the second partials test, you can tell whether you have a maximum, minimum, or saddleable point. And then you find out what your z value is when you plug in your critical points into your original function. I can demonstrate with this following equation. So I found the partial derivative with respect to x equaling to this. I set it to 0 and found my critical point for x, and it's 7/2. So I did the same thing for y. I differentiated with respect to y and found that y is equal to -8. And that's my other c point, my critical point. And I found that the second derivative with respect to x is equal to 2. The same goes for the second derivative with respect to y. And I found that this is also equal to 0. So plugging it into my equation, found that this is 4 minus 0. So essentially d is positive. And on top of that, the second partial derivative with respect to x is it's positive and it's greater than 0. So what we have here is a relative minimum. And this is our critical points. So now that we have our critical points and we know it's a relative minimum, we can plug it into our regular equation, our original function, and find the z-value, which turns out to be negative 76.25. And so we have a relative extrema, relative minimum at 7/2, -8, and negative 76.25. In here we have another problem given by this equation, and partially differentiating this with respect to x, we get this, and then we find that our x is actually equal to 1/2. So that's our critical point for x. And we found that this is our critical point for y. This is our second partial derivative with respect to x, which is -6. And this is our second partial derivative with respect to y, which is equal to -4. Plugging it in to our equation, we get that d is equal to 24, which is positive. But this time, second partial derivative with respect to x is actually negative. So what we have here is a relative maximum. Our critical points were 1/2 and -1. We plug this into our original function, and we get that z is actually equal to 7.75. And so we have, all in all, we have a relative maximum at 1/2 and -1 and 7.75 at those coordinates. Thank you guys for watching. Have a good day.